All right, everyone, welcome back. So last week we talked about distance and similarity in the context of big data. So we discussed some of the methods to kind of index the space, index the data space, so that using that indexed structure, we could accelerate the computation of the distance search. So the idea was basically to subdivide a data space and then define a means to rapidly access each of those buckets. And then whenever there's a query point, you basically visit those buckets corresponding to that query point and then do the distance computation. So that was the idea behind the KD trees and the locality sensitive hashing. So we compared the pros and cons, and in terms of the 3 V's of big data, right? So what happens in the when the volume is large? What happens if there's a high velocity of data coming in? What happens if there's a whole lot of variety in the data? So we compared and analyzed the algorithm, and then finally we saw some examples using Apache Spark where you could implement locality sensitive hashing on an actual data set. So we're still kind of going to continue the discussion about the distance and similarity today, but we're going to talk about a slightly different approach, which is called a Nystrom approximation. So long story short, Nystrom approximation does not use any kind of a pre-indexed data structure. Rather, it uses kind of it's actually a brilliant mathematical trick where you could really approximate a distance matrix from a partial computation result, so that instead of computing the distance matrix in an exhaustive manner, you can approximate a distance matrix fairly well by having some partial computation of the distances. So with that, here's something I want you to think about. Imagine you have a distance matrix D, okay? And in fancy terms, we call it a symmetric and positive semidefinite matrix. So symmetric means when you have a matrix with respect to diagonal, you have kind of a mirror image, right? So the element at ith row and jth column is the same as the element at the jth row, ith column, okay? So that's basically what symmetry means, right? And positive semidefinite means what? For any given x, this is greater than 0 or equal to 0. So positive semidefinite, so semi means it's not definitely positive. So we have an equal sign over here, okay? So whichever x you have, okay, for all x, whichever x you choose, okay, x transpose times matrix D times x is going to be greater than 0. So this is actually analogous to a positive number in the world of scalars, right? So in the world of scalars, for example, imagine a real number, okay? So you can tell if a real number x is greater than 0 or smaller than 0, right? When a real number x is greater than 0, what happens is, well, you can represent a real number that is greater than 0 by using a square of some constant. So when a value is greater than 0, then you can always find a square, okay, of some number that produces that non-zero positive value. Sorry, my email app is making sounds. So let me close that. All right. So in the matrix world, however, we don't have that kind of comparison, right? So how do you tell if a matrix is sort of like positive and a matrix is sort of like negative? How do you evaluate if a matrix is, quote unquote, bigger than 0 or quote unquote smaller than 0, right? So one idea here is, okay, in case of a real number, in case of a scalar, okay, when you multiply some unknown real number to the square of some constant, Okay. By default, we know that the square of a constant is always positive. So when you multiply a real number to the square of some number and the result is still positive, then there's a guarantee that this unknown value x is positive, right? Whereas if this multiplication is smaller than 0, then we have some guarantee that we have a guarantee that the value x is negative, right? So it sounds kind of silly, but we're kind of setting a ground to expand this concept to the matrix world. So the idea of multiplying a square of something is actually similar to the idea of this quadratic form. So instead of multiplying a square of some constant, let's consider some vector c, okay, that is multiplied to the matrix like this, okay? Now, if this matrix D is positive, then you want this value to be positive, okay? And then when the matrix D is negative, then you want this quadratic form to be negative. So that's a definition of positive definite matrix. And, this is a definition of a negative definite matrix. And semi means, it's not 100% certain. There are cases where, the quadratic form is equal to 0. So that's the meaning of the positive semi-definite matrix. So long story short, what we call a distance matrix is a matrix that is positive semi-definite. Okay, we can prove that from the properties of distance functions. Remember, we talk about those 4 requirements to be a distance function, and then using those 4 requirements, we can actually prove that a distance matrix is positive semi-definite. But we're not going to do it here because that's quite tedious. But instead, what we're going to do is to use the fact that the distance matrix, a distance matrix D is always a symmetric and positive semi-definite. We're going to use that fact to develop this Nystrom approximation. Okay. So when the matrix D has a symmetric structure, then you can write the matrix in a block structure. So, this is basically just assigning a nickname to the subparts of the matrix D. So we have a matrix D. It is symmetric, so that means the upper triangle is a mirror image of the lower triangle, right? And then we're going to just assign a nickname to the upper left corner of this distance matrix D, okay? So we're going to call this A, okay? And then this part over here, we're going to give a nickname of S. And since the distance matrix is symmetric, the mirror image of S is basically the transpose of S, okay? And then finally, the remaining portion of the matrix over here, we're going to call it a matrix Q, okay? So that's what this first line of the equation means. Now, without any proof, without any background, here's a crazy argument that is made by Nystrom. Nystrom is the name of a mathematician, and what Nystrom claims is that if we know A, which is this part over here, and S, which is this part over here, okay, if we know A and S, we can guess with a pretty good precision what the values of Q would be. Okay, and then the value of Q is determined by this relationship over here. Q equals to S transpose times A inverse times S. And long story short, this is what is called the Nystrom approximation. Okay, so it sounds like a crazy argument, right? I mean, we have a distance matrix, but some part is unknown. And what this guy says is, well, that doesn't matter. As far as I know, some rows of the distance matrix, I can still approximate what the values would be for the unknown portion. Okay. If you still don't think this is a crazy argument, think about this situation. Let's say we have a matrix D, which is, let's say, 1 million by 1 million. Okay, so we have 1 million data samples. Now, let's assume we only know the distance relationship for 1,000 rows. And by knowing this 1,000 rows of the distance matrix, I can estimate how many rows do I have. Still, there's 999,000 rows, right? That is unknown. And if this guy Nystrom is correct, what this means is I can still approximate this 999,000 rows in the distance matrix without actually doing the computation. Okay, so that's actually quite a wild argument to make, right? So here's more formal definition. Okay, now that we know conceptually what this guy is arguing, okay, here's more formal definition of Nystrom method. Given a symmetric positive semi-definite matrix D, okay, we're in the same setting, okay, what is called a rank K Nystrom approximation is defined as R transpose times the AK with this plus sign, I'm going to explain this later, times R, where R is essentially that AS matrix. Okay. Well, you can write it like this, right? And this is what is called a rank K Nystrom approximation, dk, of the original distance matrix D. Okay. Now, the AK plus over here is defined to be the summation from I equals to 1 to K of singular value, the ith singular value of A, and we flip it, so make it an inverse, and then we have the ith singular vector transpose. Okay, and that is the definition of. Okay, so U over here is the singular vector that is determined from SVD, right? And then the sigma over here is the diagonal component of that, SVD result. So the diagonal component of sigma from SVD. And, when A is relatively small, computing SVD is not going to be a big trouble, right? This is something that we saw a long time ago, right? When we first introduced the linear regression in the context of big data. And then we talk about SVD back then, right? So what it basically says is, okay, for a given A, I can do singular vector decomposition. And then as a result of that, I'm going to have U times sigma times U transpose. And the reason why we have U instead of V is because A is a symmetric matrix, right? And then from this, we can have the ith column, okay, the ith singular vector of A, right? So we're basically multiplying a column vector with itself and then multiply by the inverse of the corresponding diagonal component of sigma. And that's why we construct AK plus, okay? So it sounds complicated, but actually what's happening here is, with the SVD result, you're just dropping, the elements after the kth, the first. So we're basically taking the first k singular vectors and the singular values from SVD result, and then approximating a matrix, reconstructing a matrix A, using those first K values. And that's what this AK plus means. So the computation is actually going to be very simple because we're, essentially just taking the first K elements from SBD, right? And the matrix R is essentially just the first 3 rows of the distance matrix. And what we're going to do is to just simply multiply them. And then that is going to be the reconstructed distance matrix. Of course, if we have a large K getting closer to the total number of rows, right, then the Nystrom approximation will get closer to the actual distance matrix D. If K goes closer to 0, so it goes to a small number, the accuracy of the approximation is going to be obviously lower, okay? But the fascinating point is, for a sufficiently small K, okay, you can actually do a pretty good job in reconstructing the full distance matrix, okay, using this formula over here. Now, that was a little bit dry, and quite technical explanation of what Nystrom approximation is. More intuitive explanation of Nystrom approximation is triangulation. Okay. Imagine you have a radio tower, okay? And then, you're at one location. And then from the location that you're at, you know that which direction that radio tower is, okay? And from that, okay, we draw a line, maybe on the map, in terms of where the signal is coming from, okay? So we can then assume that the radio tower is somewhere in this direction. Now then you move to some other location and then try to measure where the radio tower is, okay? Try to find the direction to the radio tower and then draw a line in the map again. And where the two line crosses on the map is going to be the location of the radio tower, okay? That's the idea of triangulation, and that's basically what we do every day, right? The reason why we have 2 eyes is because one eye is not sufficient to generate the notion of depth, right? And with 2 eyes, now you are kind of triangulating everything, right? So left eye and the right eye, they are not on the same plane, not on the same location. And since left eye and right eye are split apart, you can triangulate the objects. So then you have a feeling of which object is closer, which object is further. So that's basically what's happening. And triangulation is essentially what we do every day. And Nystrom method, in some sense, is kind of the same idea. Okay, it's not exactly the same idea, so don't get it wrong. It's not exactly the same idea. We're not measuring the direction per se, but it is kind of like a triangulation by using the notion of distances. Okay, so here's the thing. Consider these points, and then you'll notice that the points are sort of color coded. They have different colors. I'm going to call this blue dots in the middle. It pivots. Okay. Now, what I'm going to do is I'm going to measure all the pairwise distances between the pivots. Okay. So I'm going to measure the distance from this guy to all the others. I'm going to measure the distance from this guy to all the others, and then so on and so forth. And as a result of that, I'm going to have the distance relationship between all possible pairs between these blue dots. And as a result of that, I'm going to have D11, D12, D13, D14, D21, D22, da-da-da, D24, D31, da-da-da-da-da, D34, D41, da-da-da-da, D44. It looks like tedious, but it's not a lot because we have only 4 points, right? So by measuring all the pairwise distances between pivots, we can have this 4x4 distance matrix describing the pivot. Now, I'm going to add reference points, which are the black dots over here. Now, with those reference points, what I'm going to do is to measure the distances from a reference point to all the pivots. Okay, so I'm going to measure these 4 distances, and I'm going to measure these 4 distances. And I don't necessarily worry about the distance between the reference points themselves. Okay, I only care about the distance from the pivot to the reference. Okay, so with those pivots, we had D11 through D44. That was the matrix that we created. Now with the reference points, let's say, these are 1, 2, 3, 4 in terms of index. The reference points are 5 and 6. And the fact that we're measuring the distance from the reference point to all the other pivots means we're going to compute the distance from D1 to D5, D2 to D5, 3 to 5, 4 to 5. So we're going to have D1, 5, D2, 5, D3, 5, D4, 5. We're going to do the same thing with the 0.6, right? So we're going to measure the distance from 0.1 to 6, 0.2 to 6, 0.3 to 6, 0.4 to 6. Okay. And as a result of that, we have this kind of, fat and fat and short vector, fat and short matrix that looks like this as a whole. Okay. Now, given that, let's now consider a query point. And this query point is something that we don't know yet. Okay. And for this given query point, what we want to do is to find a point that is closest to this. These are the points. So the pivots and the references are the ones that are stored in the database. And then this one is a query. And your goal is, for a given query point, you want to find the ones that are closest to the query point from the DB. Okay. So in a naive application, what you're going to do is then to compare the distance from the query to all the other points in the database, right? This is kind of a brute force manner. But using Nystrom approximation, you can actually compute the distance in a very effective manner. Okay. And that happens like this. From the query, we first measure the distance from a query to all the pivot points. Okay. And then let's call it, so this was 1, 2, 3, 4, 5, 6, right? And let's call the query point be 7. Okay. So what it means is the fact that we're computing the distances between the pivots and the query point means that we're computing D17, D27, D37, D47. And remember, in the previous slides, we have already computed this matrix over here so that the new query point is basically an additional row that goes over here, right? So we're basically doing that distance computation between the pivot to the query point. And now, as a result of that, we have a distance matrix that has 4 rows and 7 columns, right? And the first 4 columns, I'm going to chop it over here, and I'm going to call it A. And then the later part, I'm going to call it S. And using Nystrom approximation, I can fill in this component Q without actually doing the computation. And Q corresponds to what? here's this column at the end is the query, right? So that's the 7th column, which is the query column. And then the missing rows are the next 3 rows, right? And here's, well, let me be a little more precise. So here's row 5, here's row 6, and then over here is what? D57, which is the number that measures the distance from the reference point 5 and the query point 7. And then similarly, here at this location of the distance matrix, we have D67, which means the distance from the reference point 6 and then the query point 7. Okay. And since we can reconstruct this location over here without actually measuring directly the distance between the query and the reference points, we can fairly easily approximate what the distances are. Okay, so that's the basic spirit of Nystrom approximation. Now, why do we do this, right? Why do we do this? Is it any useful? Well, yes, there are reasons why people are interested in Nystrom approximation. If you think about it, in this toy example, I avoided using too many reference points because that will make the figure too crowded and very complicated. But in the real practice, you have lots of black dots. Okay. You have lots of black dots, lots of reference points. Way much more than the number of pivot points. Okay. So that means when you can do a Nystrom approximation, let me try to pick a different color. With a Nystrom approximation, sorry, without Nystrom approximation, you'll have to visit all those thousands of reference points in order to find, for example, the nearest neighbor, right? But with Nystrom approximation, you don't actually have to visit all those thousands of black dots. You just need to compute the distance from the query point to all 4 pivots, which is not a big deal, right? And once you know this, then what you can do is to automatically approximate the distance from the query to all the other black dots over here. Okay. So when you have, 4 pivots and only 2 reference points, it sounds like, kind of a dumb thing, right? To do the Nystrom approximation to approximate the distance to those 2 points. But when you have like thousands of reference points, then, that's where Nystrom approximation start to be really powerful. Okay. So with that, okay, here's yet another repetition, okay? Because I know this is a difficult concept. So historically, when I taught this concept, I could see a lot of students kind of struggle. So here's yet another visualization. So again, I'm going to use that 1, 2, 3, 4 index. And that is what corresponds to this A matrix over here. Okay. And the A matrix looks like this. Distance from 1 to 2, 1 to 3, 1 to 4. And then the reason why we have all zeros on the diagonal is because distance from 1 to 1 is, distance from itself to itself. So it's always 0, right? And then again, this part effectively, you don't really need to compute this part because it's symmetric. So D12 is the same as D21, D13 is the same as D31, and so on and so forth. And after you compute the matrix A, what you're going to do is to compute, well, the distance from the pivots to the reference points. And that's, like I said, the later part, okay, which we're going to call B over here. So B is a 4x4 matrix, 4x2 matrix, and then it's comprised of 2 vectors, each of which representing the distance from a reference point to all the other pivots. So D1, 5, 2, 5, 3, 5, 4, 5 means the distance from the reference point 5 to all the others. 1, 6, 2, 6, 3, 6, 4, 6 means the distance from the reference point 6 to all the, all the 4 pivot points. And that's our matrix B. And then finally, we have a query point, and that's we're going to call C, and we measure the distance. We compute the distance from the query point 7 to all the other pivot points. So that's going to produce D17273747. Sorry about the difference in the convention, but that doesn't matter because it's a symmetric matrix, right? So anyways, we have D17, D27, D37, D47, and B and C together constitutes the matrix S over here. Okay, so the formula that we saw from the previous slides can be written again using this matrix A, B, and C, okay, in the context of big data. Now, this unknown part over here is Q, and the ones that we're especially interested in are the distances from 7 to 5 and 7 to 6. And and that is a subpart of block matrix Q, and we're going to call it a D. Okay, so remember the equation of Nystrom approximation that says Q equals to, sorry, the approximation of the distance matrix equals to the R transpose times A K plus times R, right? Now, if we rewrite this equation in terms of this subpart of Q, this is what we get, okay? So this unknown part over here is equals to B transpose. B was what? B was the distance from the references to the pivot points, and then A inverse, and matrix A was the distance between all pairs of the pivots, and then times C, and C was the distance from the query point to all the other pivots. And the Nystrom approximation formula boils down to this simple equation that says the distance from the query point to the reference points is represented by B transpose times A inverse times C. Okay. Now, if you think about it, this is pretty nice because this one over here, A inverse, can be computed before we're seeing the queries. Okay. Because, well, let me go back one slide. Because if you think about it, these are the points that are in a database, and this is the point that is, query in online. So everything about these points in the database can be computed offline, right? So with that said, A inverse, which is the distance matrix among the pivot points, can be computed in offline without having to worry about what's going to come in as a query in the future. And same thing, the distance from the reference to the pivots can be computed offline as well without having to worry about what's going to come in the future as a query. And that means you don't really have to compute this all the time, but instead just pre-compute this value, B transpose times A inverse. And then in online, whenever there's a new query come in, you just quickly estimate the distance from the query point to the pivot 1, pivot 2, pivot 3, pivot 4. And that can be done fairly quickly, right? And then construct a matrix C, and then multiply that matrix C with the pre-computed B transpose times A inverse. And with that, you can in real time estimate the full distance matrix D that gives you the information. Sorry, this is confusing. This is not the full distance matrix. The distance from the query to the reference points, which are unknown at the moment, right? Because we computed only the distance from the query to the pivots, but we never computed the distance to the references. And those unknown information can be estimated without any direct computation. So it becomes just a matrix multiplication problem, which can be done much quicker compared to the actual exhaustive distance computation. Does it make sense? By the way, I'm keeping my eyes on the chat box, so if you have any question, please let me know. There's actually one. Can you post this annotation with on icon? Yes. So I'm going to post this video online. I know I'm pretty slow in posting the videos, but all the annotations and everything is going to go up on icon. So with that, there are several things that you need to decide as a designer. First of all, how many pivots do you like to have? Well, the more pivots you have, okay, so let's think about the meaning of this. So matrix A is, the matrix A concerns with the size of the pivot, as well as, now let's use the ABC representation, right? So if you grow the size of matrix A, that means you know majority of the distance matrix, and then the unknown portion is fairly small. Whereas if you have only a small number of pivot points, that means you have a vast majority of the distance matrix remaining unknown. So what do you think? Is it better to have a large number of pivots, or is it better to have a smaller number of pivots? So obviously, if you have larger number of pivots, then you're going to have a better approximation because you already know a large number of a great portion of the distance matrix, and the only thing you need to approximate is, you know, a small fraction. So it's going to be easier, right? You can intuitively say that, right? Versus if you have a small portion of pivot, then it's not going to be that easy, right? And therefore the accuracy of the approximation is going to be fairly low. So as many as possible pivots means you have a better approximation. But obviously, if you have a situation like this, you don't really take the advantage of Nystrom approximation. The whole point of doing Nystrom approximation is to avoid computing the full distance matrix. And if you already have a great portion of distance matrix, you know, computed already, why would you bother to do Nystrom approximation, right? So that means in order for a faster computation, first of all, you want to use as small number of pivots as possible. And that also means, you know, in terms of memory consumption, you also want to have as small number of pivots as possible. Because again, look at this matrix over here. You don't want to store the entire distance matrix, and you want to keep it, you know, as succinct as possible. So it's always kind of a design decision that you have to make as a data scientist before to use, you know, before to develop an application using Nystrom approximation. Do I want to go with 1,000 pivots? Do I want to go with 100 pivots? Do I need to do like 10,000 pivots, right? So by considering the size of the problem, you have to make a decision, okay? But, you know, usually, this is kind of a hunch, but usually 10% is kind of the starting point. You know, somewhere between 5% to 10% is kind of a starting point. Empirically, there's no scientific evidence, but empirically, that's kind of a good starting point. And then you can conduct an experiment by increasing and decreasing the number of pivots and see how the accuracy changes, which is, by the way, an exercise that we're going to do today. Okay. So in order for that, here's an example. This is what is called an abalone data set. So abalone is this weird creature that lives in the sea. This is one of my favorite, which is quite popular, I think, on East Asia. But I guess you don't find abalone in Iowa, so it's kind of too bad. But that's what this thing looked like. Okay, this is sort of like a shellfish. Okay, and interestingly, people found that the age of abalone is a function of those 8 parameters. Okay, so the first parameter is a sex, male or female or infant. So those are the 3 values that each abalone can have. Length is, how long the abalone is. Diameter is diameter, how large abalone is. And then height is a height. And then there are a couple of weight measures. So whole weight is like the weight of the abalone, not only the meat but also the shell. Shooked weight is the weight of the meat itself. Viscera weight, shell weight. So those are the parameters that describes abalone. And then people found that there was pretty good correlation with the with this 8 parameters with the age of an abalone. And the age of abalone, interestingly, can be captured by counting the number of rings. Okay. So similar to the trees, abalone develops a ring, like a geometric rings on the shell. And then, by counting them, you can estimate the actual age of abalone. So that is going to be the output parameter in this abalone dataset. So the goal over here, the mission here is, for a given these 8 features, which are the ones that are, can be similarly measured, predict the age of an abalone, okay, by using this correlation in the database. And our game plan is to use k-nearest neighbors. Okay, so what we're going to do is basically, let's say you have, lots of abalones in the data set, and I'm, representing the feature space. So this is an 8-dimensional space where the abalones are distributed. And then let's say there's a query point over here. What I'm going to do is to measure the distance from the query point to all the other points, and then find the ones that are closest to the query point, right, which is the k-nearest neighbor. And then we're going to take the ages of those nearest neighbors, and the average of those neighbors, the average age of those neighbors is going to be the prediction of the age for the query point. Okay. So before we actually do this, okay, here's kind of my pre-experiment. Okay. So like I said, we're going to use a K and N. And then the way that I structured the data set is I randomly split it roughly 70% of the data samples as the training samples. So we have roughly 3,000 abalones being used for training of the K and N. Well, it's not really training anything, but, and then randomly selected 30% of the data, which is approximately 1,200, are being used for testing and validation. Okay. Now, without showing how I implemented, okay, this is the result of naive KNN approach. Okay, the horizontal axis over here represents K, so how many neighbors I'm using for making predictions, and then the vertical axis is the accuracy of prediction. Okay. And more precisely, this is an accuracy in terms of the percentage. So 1 means we are 100% times accurate in predicting the age of abalone. Okay, and then accurate or not is defined within the tolerance of 2 years. So the age prediction, if the error of age prediction is in between the range plus minus 2 years, then we consider that as an accurate prediction. Otherwise, we consider things as inaccurate prediction. Okay. And here's the chart showing the relationship between the number of neighbors K and the prediction accuracy. And as you can see, somewhere around K equals to 6 to 10, we have pretty high accuracy. And then obviously, as the K grows, you can see the trend that the accuracy kind of going down. Right, that's kind of straightforward, right? Now, that was the naive implementation without using any fancy trick. It was an exhaustive distance computation. Now, here's the result using only 10 pivots. So if you think about it, there are about 3,000 reference points, whose distances are not known, right? And only with those 10 points, here's the performance of K and N, okay? Again, with the same scenario. So we have the accuracy versus K graph again. And if you see over here, in the previous slide, we had roughly 80% accuracy. Now, in the Nystrom approximation case, we have slightly lower accuracy. We have around 73%, I guess. Okay. So clearly, it is not as good as the naive computation in terms of accuracy, right? Because there was about 7% of drop. But if you think about it, this is still kind of favorable result, because if you look at the computational time, it is about a ½ second versus 0.1 second. Okay. And of course, we have only roughly 3,000 samples in the training data set. But if you consider a real world big data scenario where we have not only 3,000, we can have 3 million data points. Imagine what the difference is going to be when n is much greater than 3,000, right? So, and remember, we're using only 10 pivot points. And in the next class, we're actually going to experiment with our own code to see what happens when we have a varying size of pivots. So of course, with the 3,000 training points and only 10 pivots, it is actually too little if you consider the size of the data. But even with that, this is the range of accuracy that we could actually achieve, as opposed to the naive method. So I can say it's actually fairly good, right? Because we only have 10 pivots where we know the full distance matrix, and then the vast majority of the distance matrix is unknown. And despite the fact we were able to approximate the distance fairly well, and using that, we could construct a k nearest neighbor classifier that is nearly good as the naive KNN approach.